We start with a little bit of a theory about the DLS. You have to look up the files that I've sent you some time ago about the synthesizer. So the file is called something like this: synthesizer customer on-site training course dynamic light scattering 2019. And this is the file that is in question. It's got quite a few slides on it. It's a really good file. It gives you quite a lot of information about the DLS and the way it operates. So it's good to look at the theory before you start analyzing to make sure you understand what is happening. But effectively, what you receive when you're doing the analysis and measurements is you get this correlation function. And this correlation function in itself has a lot of information ingrained in it. So again, it's something that we'll be going back to it, and you should be looking at the correlation function really a lot as well. So it's good to review those information about it. But how you're analyzing the correlation function is the synthesizer software does it for you in two ways. One is the cumulance analysis, and the other one is distribution analysis. And they're two quite different, and you have to be aware of the advantages and disadvantages of using them. The cumulance analysis requires you to have fairly monodisperse particles, which means that the polydispersity index is fairly slow, fairly narrow, and you need to know very little about you just need to know dispersive refractive index and the viscosity. And as a result, you can then use the Z average. So you have an example here of a peak that would be, a sample that potentially would be very good for cumulance analysis. But your silver nanoparticles are not suitable for it because, as you might have noted, on the distribution analysis, on the distribution of your measurements, usually have 2 or sometimes 3 peaks as well. So actually, you should be looking at the distribution of sizes analysis rather than just Z average. The problem with the Z average is that it will give you a false result. So if you have 2 populations, one of 100 nanometers and another one of 50 nanometers, and they're mixed together equally, if you have the Z average will tell you the average is 75 between the two, but actually you don't have any 75, you have hundreds and a 50. So relying on a Z average can be extremely difficult, especially in your circumstances when you have a multimodal particles distribution. And so your polydispersity index is here within the mid-range value most of the time, but the software will also tell you whether it's good or not good for cumulance analysis. So, and this is the example I just showed you. So the Z average would show you that actually the average of those 2 populations is this, was actually have 2 multimodal samples. So you have to be very much aware of that. So a distribution analysis is a little bit more complicated, but effectively what you're doing is you're looking at the population and how they change. I'll show you some more examples using your data anyway. So what we are looking at now is the data interpretation. So data interpretation, you have to start by selecting the right parameters in the synthesizer software. So you got to have those parameters here, such as derived count rate, attenuated measurement position, in range measurement, intercept, fit error, multimodal fit error. It's important that you get them. I have showed you how to do this when I was setting you up in the lab, and I don't know if you were able to do that on your own computer or not. So just briefly, you can change them here. So you click on the tab here, and you go record view parameters, and so you can add them and remove them. So for example, you might have to go through a little bit, but most of them is in size or aggregation or details. So for example, in size, we're interested in cumulants fit error, or you're interested in range. So you just go click here to add, and they will come at the bottom. And if you want to remove, you might have some redundant ones, such as size peaks. You might want to remove those. So you just click here and remove them, and you can move them about as well, up and down on that screen. So you get this kind of level of information that is required to be able to start the data interpretation. The parameters you want are named here. It's a slide 60 of that file, and the reports, you should have all of them here. So you should have those intensity, volume, quality reports, as well as parallelogram and cumulants fits as well, and distribution fits. I'll go over them in a little bit more details a bit more. But for example, if you go to size quality report, it will give you the problems that you're having with your sample straight away, and what are the issues. So there is some initial information that you can get from those reports here. And so the first step will be to look at, rather than looking at sizes of those particles, to look whether the quality of the data is good. This is the first thing you have to understand, and you have to be able to present in your report. Where is the confidence coming from to the fact that you're able to use the data and it's a good quality data? Okay, and so the first things you're looking at is, if you select your samples, you're able to you'll have your mean and a standard deviation at the bottom. So I'm looking at all those parameters pretty much across, and I'm looking what the standard deviation is on those parameters. If there's too much standard deviation, it might mean that the data isn't reliable. And in my experience, is the more PHMB is, the trickier it gets. So for example, if you look at the bare silver nanoparticles, or even the 20, the standard deviation is fairly small. We're talking about, singular items that are deviating there. But actually, when you look at 100, this deviation is a lot bigger. So that is a suggestion that there is something happening over there. And it's in your responsibility to be able to make sense of those information. Those parameters are described in that file that I've sent you. Obviously, you can't really reference it in your report. You should go and find literature that discusses those parameters. But in essence, for example, the general rule is if the in range should be above 90, it's 90%. So those that are below 90, so all these are potentially of poor quality. And you can see how much the standard deviation is on the size of those silver nanoparticles. So it's 66, but actually the standard deviation is 60. So that's showing that there is something happening with the sample. And what might be happening with the samples are a few possibilities. So the samples might be aggregating, or they might be sedimenting, or there might be falling apart. So in general, we call this number fluctuations, and you should look at whether the number fluctuations are a problem in your case as well. One of the ways to look at this as well is to look at the correlogram. So that function that you get as a direct measurement of this scattered light that gives you certain information about the sample. So it could be that if there is a pattern of how this sample is, reducing, for example, its intercept, or it's increasing the intercept, there might be an indication that it's sedimenting, or it's aggregating, or that is breaking up as well. So again, you need to look at this and see on individual case-by-case basis, understand what is happening there. So now when you go into a data analysis and looking across the different measurements that you took over the number of weeks, one of the things that you can look at is the change in the quality of the data. So if you notice that there are some changes, so if you noted, for example, at the beginning that the quality of the data for certain measurements were not good, you might have noted that it's because of sedimenting or aggregating or any other issue there. You can look again at the same sample a week or 3 weeks later, depends on the data you have, and understand whether this change occurred in the quality of the data. So whether the sample is again sedimenting, aggregating, breaking apart, whether this quality of data can now be relied on, or still is below the quality that you would want it to be. With that, you can look at how much of the changes, because for example, parameters like in range will give you a percentage value of and whether there is a change in that in range value or not. So the first step in the data analysis would be now analyzing the change in the quality of data between your initial samples and then subsequent repeated measurements that you took over the weeks, over the course of the project. And then once you believe that your samples are good or of good quality, so for example, let's take the 20 PHMB silver nanoparticles, which do appear to be fairly consistent. So the runs are overlapping both here in the intensity and here in the correlogram. It's a pretty good fit. And it says that data meets quality criteria. This is because I selected more than 6 samples. So when more than 3 samples, sorry. If you select more than 3 samples, you will be analyzing whether these samples are similar to each other or not. The software automatically does that. But you look at those samples and now you can see that you can rely on probably not on a cumulance analysis, so not necessarily on a Z average, because you still have fairly polydispersed sample with a Z average, but you have multi-model. So you should use a distribution analysis. And effectively, what you're looking at is the 2 populations that you've got there and how much they part or how much they contribute towards the distribution of the scattering light by intensity. One of the reports that I didn't mention is a model size report. It gives you a little bit more information about if you wanted to change into volume and number, but I wouldn't be worried about it too much at this stage, because volume and number gets extremely difficult very quickly, because you have to understand the maths that is behind it as well, and the calculations and the limitation that it comes with. So if you do get into theory and you start investigating and you find that you want to use that, let me know. I'll be more than happy to explain more about the volume and the number. But looking simply at the intensity, you can see that there are two populations, one with around 114 peak size, and the standard deviation for this is about 58 nanometers both sides, and then a smaller population of around 19, 20 nanometers, and a small distribution into both sizes. And so these are important information that you can rely on rather than the Z average, because we established that this is a good quality of data. And so this is how the analysis would work for you. Is there two types. One is the quality and the change in the quality of data. And then once you reach certain level of quality of data, you should be able to rely on that data to discuss this further. I mean, just simply looking at this, this is your file. This is second batch characterization that I just opened up. I'll think that 40 is fairly okay. It's not good for cumulants because the cumulant fit error should be below 0.005. So it's not very good for that, but it should fit into the multimodal error, and the multimodal error is the distribution analysis. So again, you know, this fits very well. This is a little bit more difficult around there as well, but the quality of data might be good enough. And here again, you know, how good is this data? There is something happening here. So the fit here, the overlap here is very good, but the overlap here, there's something happening, and it could be an indication of something. So it's worth to look into this into more details as well. The big peak, you could probably call it pretty much the same. The small peak is even more, is getting more complicated. So there are some patterns in there that you can discuss. Obviously, the further you go, the more hectic it gets, really. But this should get you start going pretty well with even with the amount of data that you've collected. You should be able to do those things, which is changing the quality of data. And so first analysis is the quality of data itself, then changing the quality of data, and then for those samples that you can rely on the results, then you can do the sizing analysis, so distribution analysis.